So we were learning different types of laser. So in the previous lecture, I told you that there are several different types of laser, and we can categorize them into different sections like solid state laser, semiconductor lasers, gas lasers, atomic as well as molecular gas lasers, chemical lasers, dye lasers, and so on and so forth. So today we are going to look into different types of laser belonging to these different categories. So we'll start with the solid state laser, and the first one that we will look at is the ruby laser. So ruby laser was the first laser that was invented. So what is a ruby? Ruby is a crystal. I mean, most of you are aware that this is also regarded as a gem, and it has ornamental use, and it has a beautiful color which is known as ruby red color. Now, what is the origin of this color? The origin is actually because of some impurity, impurity of chromium ions in an alumina crystal lattice. So without this chromium impurity, the alumina crystal will be just colorless, whitish. Now, a very little amount of chromium ion, that is essentially present as Cr2O3, and it exists in ruby by approximately 0.05%. So you can imagine how little it is. But this little amount of chromium does the work, be it its color or be it in the application in laser. So this particular chromium ions, they provide the states, electronic states, that can give rise to population inversion and hence lasing. So what is actually done? So this chromium ions, which are essentially chromium 3 plus, sitting in the alumina lattice, they are excited by a broadband light source. So from a flashlight. So flashlight can have a huge range of wavelength. So it can be like white light, and that from that white light, these chromium ions, they can take up the photon and go to certain excited states. Now these flash lamps, they can be placed either parallel to this ruby crystal. So like ruby crystals, how do they look like, we will show in a bit. So essentially if you put this ruby crystal, which is as a rod, and the flash lamp just side by side, and this flash lamp continuously excite this chromium within this ruby crystal. Or what you can do, you can have this flash lamp as a spiral. So now what happens during this optical excitation? So on your screen you can see the energy level diagrams for this ruby, okay, which is essentially sitting in the alumina matrix, the chromium sitting in the alumina matrix. So there are certain term symbols provided here. So right now you don't worry about the particular term symbol. Many of you may be already aware of this one, but this course doesn't allow us to go through the detail of this term symbol. So take it as a a symbol which is given to particular electronic or other states based on some logic. So their energy levels are given by E1, E2, E3, E4, so on. In case of ruby, we have identified 4 such states, this 41, 42, 2E and 4A2. So though it has 4 levels, but it can be considered as a pseudo 3D pseudo 3 level system. Why? Because this 2 states, that is 41 and 42, both of them actually decay very rapidly to the state 2e, that is here. So, initial excitation is will take the molecule either to this 42 or to 41, but both of them will rapidly decay to the state 2e, and this 2e is the metastable state. So, the population inversion is created over the time, and once the population inversion is created, then a spontaneous emission can trigger the stimulated emission, and the stimulated emission can come out from the laser cavity as a burst. So, once this population inversion is lost, then again it will take time to create the population inversion. So, this is kind of inherently pulse laser. We already have talked about this one. So, this was about the energy level diagram of this system. Now, as I was saying, how experimental it is done. So, this ruby crystals, they are like an elongated rod. So, if you place this ruby rod and this lamp, which is like a tube, linear tube, side by side, then they can this lamp can excite this ruby crystal. Now, also you can have a geometry like spiral. This one also I was just talking about a couple of minutes back. So, the spiral will surround this ruby crystal, so that enough excitation can be provided to the ruby crystal. Now, there is something interesting here I would like to point out. So, we know that a cavity is given like between two mirrors, right? So, this is my cavity, one is high reflector, another is output coupler. So, this will define the axis of the laser cavity. Now, the active medium which is emitting photon, okay. So, first the flashlight. So, the flashlight is suppose here, okay, and my active medium is here. So, this is my active medium and this is my flashlight or flash lamp. So, these are giving light to this active medium, but this is giving light to every other direction, right? Now, maximum amount of light will be lost. They will not reach the active medium if this is the only configuration that I have. If I have this two mirrors, active medium, flashlight, so most of the lights that flashlight gives us will be lost, and that is a quite big amount of loss, because we are providing energy to the flashlight, and the flashlight is giving this energy in form of light to the active medium. Now, if all the energy that we are pumping into the flash lamp is not being converted or not going to the active medium, then definitely this is not a good thing from energy perspective. So, we need to arrest this loss. How can we do that? If we have a mechanism by which, if there is a reflector and this light can be reflected back into this system toward the active medium, then we really can bring down the loss to a great extent, okay. So, in practical world, exactly that's what is done. So, this, if you look at this picture, so this ruby rod and the flash lamp, both of them are put inside a reflector chamber. So, you can see that this, as if there is a jacket of something around this ruby rod and the flash lamp. This jacket is essentially reflector. So, this is a curved reflector. So, it's like a tube, hollow tube, whose inner sides are all reflectors. So, you can imagine like it's as if there is mirror inside this one. How you can do that? If you can polish the inner part, or for that matter any surface of some metal or metal coated surface, then by the very own property of the metal, it can be highly reflective. Metals like gold are often used for this purpose. So, a gold coated surface, so essentially you have a tube, hollow tube, and inner side walls are gold coated, and that can really reflect the lights coming from the flash lamp with a high degree of reflectivity. So, efficiency is very high, and the light goes back to the active medium or toward that. Now, so that is about in this direction. So, now one more thing one has to consider. Even if I think about reflector all around this lamp and ruby crystal rod, it is not necessary that the reflected light will reach the active medium, that is ruby. So, we have to think about a particular geometry which can certainly do that. So, that is the reason that this hollow reflector is made in a way that a cross section of this hollow reflector looks like an ellipse. Actually, it is an ellipse, and this cross section, so if you take a cross section along this, that is shown here. So, this is an ellipse, and the ruby crystal and the flash lamp are kept into the foci of this ellipse. What happens is given in this picture. So, the flash lamp gives light. Okay. So, the light can directly go to the ruby crystal. So, it can go directly here, but most of the light will go away, correct. Now, wherever it goes, because of the geometry of the ellipse and its foci, it will come back to this particular place. Okay. So, a simple knowledge of geometry will tell you this. So, we are not really losing light from the flash lamp, and the efficiency of excitation is increased by a great amount, and this is very, very necessary, because if you recollect in our first couple of weeks lecture, when we said that creating a population inversion in this kind of a 3-level system is really hard, because it needs very efficient pumping. Otherwise, because the ground state is involved in the laser action, creating population inversion is really, really difficult. So, we need to pump really hard, and if I need to pump really hard, I have to make sure that the pumping source, that is a flash lamp, doesn't lose most of its light unnecessarily, and this kind of elliptical reflector geometry ensures that we have a highly efficient reflection system. Okay. Now, here on your screen you can see on the left side I have given an image of ruby crystal. So, it has the usual ruby red color, and here particularly you can see that this ruby crystal is to some extent transparent. Okay. So, for a given light, this is definitely transparent. So, this ruby rod is placed inside a cavity. So, one side of the ruby rod essentially attached to the high reflector, and this coil of flash lamp surrounds it, and also you have the other arrangement where you have a linear flash lamp lying side by side as if they are sitting at two foci of an ellipse. Okay. So, this is the actual arrangement of the ruby laser. Now, there are few more things about this. We have already told that the initial excitation ultimately goes to the state 2E, creates population inversion, and then from there it lays. So, some practical consideration, that is what is the frequency of the light coming out of ruby, what are the pulse duration, what is the pulse energy and all. So ruby laser gives a particular wavelength of 694.3 nanometer. Okay, that is equal to this gap. So this is 694.3 nanometer, and the beam duration is pretty long. They are like 0.323 millisecond, and the pulse delay can be really long because it takes time to build up the population, and the pulse energy can be really high. Okay, it can be even 200 joule. So next we will talk about Nd:Arc laser. Like in the case of ruby, where the alumina was just a host and chromium was playing the role of providing states for the laser action, here neodymium 3 plus ions, they actually gives us the states for laser action. Here, or yttrium aluminium garnet, which has this formula Y3Al5O2, it just acts as host to this neodymium 3 plus ions. So this energy levels of neodymium ions are naturally they are degenerate. That means several states are there which has the same energy when you do not perturb the energy states. Now there is something called crystal field theory, where it is said that if you provide a crystal field to this energy states, this degeneracy is lifted. So before providing any field to it by the surrounding environment or any approaching ligand, the states are degenerate in neodymium 3. Once a field is applied by say this yttrium aluminum garnet, they become separate. Now there are several energy states in a neodymium system. Now we will look into this particular energy state diagram in a bit. Now the transition between components of 4F3 by 2 and 4I11 by 2 states, which are forbidden in the free state, that is when they are still degenerate. Once the field is applied and degeneracy is lifted, they become allowed. Fine, and ultimately these two states get involved in laser action and they provide laser emission. So here are the states that I was talking about. So initially this particular state, if I can just show, so this is 4I11 by 2 and 4F3 by 2. So this is one and this is one state. So before we had this crystal field effect, this was degenerate, and several energy states were at the same energy, and once the field is applied, they are split like this. Now earlier this transition was forbidden. Now this transition is allowed. Okay, or transition to and from. So if you are considering any transition from say this state, so that is 4F3 by 2 to 4I11 by 2, essentially this is the one which was earlier forbidden. Now once it is lifted, then this becomes allowed. So these are now allowed. Okay. So what happens once we provide light energy, provide photons from the flash lamp, just like in case of ruby laser, the Nd3 plus ions, they make transition from the ground state to 4F9 by 2, and from there it rapidly decays to this 4f3/2. So, this is the rapid decay. Okay. So, now from there it can come back radiatively to this 4I11/2 states, which are now split states after the crystal field is provided. So, you get laser emission due to the transition from this 4f3/2 states to 4I11/2 states. So, now I will show you how an Nd:YAG laser is constructed, how it looks like, actually. So, this is the region. So, this part is the heart of the system, where you have the Nd:YAG crystal and the flash lamp, they are kept. So, here also the same technique is used, that is, you wrap this flash lamp and the Nd:YAG crystal in a elliptical reflector tube. Now, there are some practical concerns. This flash lamp is flashing and it gives very high amount of photon intensity. So, you can understand that the amount of energy is provided is very high, and that gives rise to heat, and one has to cool down the Nd:YAG crystal, which senses that heat. So, how do you do that? You have to put this whole system in water, and you have to flow the water. So, what is done? You pump in water, and then you take out that water, and you have to maintain the temperature of the YAG rod. So, this flashlight will create lot of heat, and you cannot allow the heat to increase. You have to maintain the temperature, because all these state population, they are also affected by the heat. So, the performance of the laser will be degraded if this increasing heat is not taken care of. So, you do this by flowing cold water through that, and you maintain a certain temperature, normally like 18 to 20 degree centigrade. So, many occasions what you need to do, you need to couple this water circulation system to a chiller unit. Okay, but the modern days lasers, they are quite efficient. So, just circulating water without coupling it to a chiller unit is sufficient. So, these are called air cooled laser system. And apart from this active medium and flash lamp system, the Q switch is essentially placed within the laser cavity. So, the laser cavity is comprised of this high reflector. So, this is the rear mirror or high reflector right here, and you have the output coupler up here, and this part is essentially not actually a part of the cavity. This is some extra. So, up to this you have the cavities. So, from this region to this region constitute my cavity. So, this Q switch here, it contains the Pocal cell, okay, and polarizer combination. So, after the cavity, the beam comes out, and there you can do whatever engineering you can do with that particular beam. You need to expand, or you want to shrink the beam, you can do everything. Okay, if you want to convert the wavelength of the light to some other thing, you can also do that. You can do using something called nonlinear optics. So, those parts are done outside the cavity. For safety, most of the time, the some extra portion is also covered outside the cavity, where you have these extra elements which is used to say expand the beam or shrink the beam, or converting the wavelengths to another, all this. And here in this particular case, an explicit laser system, a real laser system is shown, where you can see the water inlet outlet system, okay, and this is the position of the rod, and the other side it will be lamp, and water will be circulating through these pipes, okay, and you can see explicitly the place where the polarizer is kept, the Q switch is kept, and the output coupler immediately. And you can also see that the color of the light is green, although the Nd:YAG Glazer it gives a wavelength of 1064 nanometer. So which means that inside this one you keep another crystal which can convert that 1064 to a visible green wavelength, which is 532 nanometer. When we talk about the application part, we will talk about how this can be done using the laser. And this particular image tells you that this is a Q switch laser, so it is a pulse. Now in this particular picture you cannot see any pulse output, but here you can nicely see that they are pulse. So like they are coming like a bunch of photons at a time, and then there is no photon. So you can take that picture by using an appropriate camera. So that camera shutter speed has to be synchronized with the pulse repetition rate. So in that way you can actually see this pulse train flowing. So now a little bit detail into this Nd:YAG system. So this 4F 3/2 levels which are initially populated due to the non-radiative decay from that higher level. So next step, what happens? You have an emission due to the jump of this ND3 plus system from 4F 3/2 to the 4I11/2, giving rise to 1064 nanometer near infrared laser light. A few practical things about Nd:YAG laser, that it is a very high power source of high power light. Of course, the power can be controlled, but you can go beyond 200 watt, which is like really powerful, and you can operate it in continuous wave mode. It is like a 4-level laser, and it is actually a 4-level laser. If you look at the energy states, you can see that the transition is taking place between this level and this level. So the ground state is down somewhere here. Okay, so this is essentially a 4-level kind of system. Okay, and you use Q switch to create the pulsed output, and in case of pulsed operation, the energy still can be quite high as 100 joule. Okay, so we will continue discussing about other types of lasers in the following class. Thank you very much.